Okay, good morning, everyone. Am I audible?
Good morning, sir.
Yes, just wait 1 minute, then I'll start because right now many of students are not joining. My whiteboard is visible, all of you?
Yes, sir.
Okay. Okay, so let's start. So we have discussed in our previous classes, there are sensitivity, okay? So what is sensitivity and what is the basic application of the sensitivity? And we have to discuss different combination, that is the open loop control system and as well as also closed loop control system for the forward path transfer functions and also feedback forward path transfer functions. Okay, so today we will discuss, it is another one, this is the control actions. Okay, and this part, it is very important, control actions. So what is control action? So we have certain give idea, that is the automatic control part. So this automatic control system, basically it is used to maintain the output within desirable limits. That means the different types of control actions we have to control by the automatic control system. So any deviations from the output, from the reference input, it is detected by the error detectors. Okay, so that means an automatic controller that means a automatic control system is used to maintain, is used to maintain its output within desirable limits. Limits by means of a control action. And this deviation of the output from the reference input is detected by an error detector. Okay, this is detector. This error thus detected is used as an actuating signal actuating signal for control action through a controller. Through a controller. And this proportional control action and types of control action used for improving transient. We know that we have discussed in previous more classes is a transient response analysis and also the steady state response. Steady state response of a control system okay. So this is basically one control action. So I just elaborate these things also. So any automatic controller part, okay, that means automatic control system, it is basically used to maintain its output within the desirable limits by means of a control actions. Okay, so when we have to use different types of control actions, it is basically we have to use as in automatic controller part. So any deviations of the output from the reference input is detected by an error detector. We know that this error detector, what is error detector? This error detector is detect the any error or any disaverages value is coming in the reference input to the measurable inputs also. Okay, so this is error detector. This error has detected, it is used as an actuating signal for control actions through a controller part. And these proportional control actions, that means the proportional controller part or any other types of control action, that means proportional controller, derivative controller, okay, proportional integral controller, PID controller, that is proportional integral derivative controller. So there are different types of controller part. We have to use this proportional control action and the various types of control action used for the improving transient and steady state response of a control system. Okay, so what is the basic definition of the control action we have to know, and what is the basic applications of these control actions, that is a different controller part, improving the transient response and steady state response. Okay, is it clear, all of you? Is it clear? So we know,
Yes, sir.
different types of control actions. First, proportional. This is proportional control or P control. This is proportional controller part or proportional control. This is P control. Then derivative. Derivative control, that is D. Number third, integral control. This is I. And another one, this is PID, that means proportional plus derivative plus integral control. Okay, control. This is PID. So these four types of control we have to know, that is the proportional control, that means P control, derivative control, that means the D, and integral control, that is the I, and also proportional plus derivative plus integral part, that is the PID controller part. And sometime also we have to know that is a proportional integral controller. This is another one, P for proportional controller part, and also I, that is the integral controller. So we have to always also use that is a proportional integral controller part. Okay, so these are the different types of control actions we have to use this in our control systems or industries. First, we have to start from the proportional controller part. Is it okay, all of you?
Yes, sir.
Okay, next, first we have to know that is proportional control. Proportional control. So first I am drawing a one diagram. This is summing point. This is first block, that is a control actions part. We have to denote here K. Then another process or plant we have to express, that is GS. Then this is the output. And another one, feedback loops is also present. When feedback loops we have to attach, that means this is the closed loop control system. We know that this is connected this summing point also. This is negative and this is positive. So this is ES, we know that, that means the error signal. This is the error signal. And another one, that is the input, that is a reference input signal. We have to denote RS. This is the reference signal, or sometimes it is also called reference input, or a single, that is the input of the control system. Okay, and this is basically, we know that feedback signal, which is connected output to the summing point also. And when the controller part, we have to calculate it from here, this signal, it is called the actuating signal. This is the actuating signals. Okay, so this is a basically block diagram of proportional control actions. And in this control action part, one question is very important for your semester, that is the university's exams. Okay, so one control action, it is also coming in your semester exams papers. So please understand this carefully. So this is block diagram of proportional control actions. Or
excuse me, sir.
Yes. Yes, hello.
Sir, hello.
Yes, bolo.
Sir, is a proportional controller provide continuous control or discontinuous control?
No, this is a basically one closed loop control actions. Okay, this is also when you have to uses in closed loop configurations. This is basically one continue proportional control actions. Okay, that means you have to, that is user set up the timing, that timing, this proportional control action, whatever we have to use it, that is a P control, derivative control, PID control, this time being oriented, this proportional or derivative or any others controller, it is time being oriented is working. Okay.
Yes, sir.
Okay. So this is proportional controller part. So just I just elaborate this thing. This is a block diagram of proportional controller part or P controller part. This is the reference input signals. Here we have to apply, that is the RS. Okay. And another one, this is a summing point we have to attach. This summing point, it is basically connected across the one error signal part. Another one is a feedback signal part. And this feedback signal path, it is connected, that is the HS, this is the feedback block to the output to the first summing point also. And this is the error signal we have to denote it here, that is ES. We know that this error signal, it is a difference between the reference input signal and the feedback signals also. Okay. And this is a control action, that is a constant control proportional control part, and this is also K, and this is when these signals, it is sends the signal, this is basically actuating signals. Okay, that means this actuating signals, this is basically proportional to the error signals, and this is the basically process or plant we have to denote it here, that is GS, and this is the corresponding the output signal we have to receive from here, that is CS. We know that the transfer function of any closed loop system, that is CS by RS, that is equals to GS by 1 plus GS HS. HS is the feedback path, GS is the controller part. So this is the basically block diagram part of the proportional controller part. So In proportional means that is a P control. Okay, I am just short terms used. So in P control, that means the proportional control, the actuating signal for the control action in a control system is proportional to the error signal. Is proportional to the error signal. So first we have to know in this proportional controller part, this actuating signal for the control action part in a control system, it is proportional to the error signal. That means the ES. Error signal, that means ES. And this error signal, we know that the error signal being the difference between the reference input signal and feedback signal obtained from the output. From the output. So we know that. So this is another terms. This error signals, that is ES, it is calculated between, that is a difference between the reference input signal, that is RS, to the feedback signal, that is the HS, from the output sections. And another one, the actuating signal, is proportional to the error signal. So therefore this system, it is called, therefore this system is called proportional control system or P control. Okay, so I just recall them. So in this block diagram part, we know that here three types of control signals we have to control. That is first one, that is the error signal. This error signal in the proportional control action is actuating signal for the control action in a proportional to the error signals, that is ES. And this error signal, it is difference between the reference input signal to the feedback signals. Okay, to the these feedback signals, it is connected across the output of the systems from here to and this part. And also actuating signal, this actuating signal, it is the basically proportional to the error signal. Okay, so this system, it is called the proportional control system or proportional control actions part. So in this desirable that control system is under damp conditions. Okay, so we know that under damp, over damp or damping factor also in our previous classes also. So this under damp control system, it exhibits the exponentially decaying oscillation in the output time response during the transient period. Okay, so this is another point. Just wait. So an overdamp control system exhibits exponentially decaying oscillations in the output, sorry, time response during the transient period. Transient period. Okay, so this under damp control system, it is basically exhibits the exponentially decaying oscillation in the output time of the response during the transient response. Okay, so those who have not attending the previous classes, that is a transient response analysis of the different control system, that is a first order system or second order system, and also we have to discuss the steady state response in previous classes. So please go through the previous classes in the in your our departmental video channels, YouTube channels. So please clarify the idea in previously we have to discuss. So okay, my whiteboard is visible, all of you?
Yes, sir.
Okay. So previously we have to discuss, this is the proportional controller part. So this overtime response of a control system, it can be made by the faster, by the increasing forward path gain in the systems also. So this increase in forward path gain of this reduce the steady state error. So I am telling the previously, the basically control actions we have to use is the control of the steady state response, and another one is the transient response also. Okay, so this performance of this control system is convenient adjustment has to be made between the maximum overshoot and also steady state error. Okay, so just wait. In proportional control, a convenient adjustment has to be made between the maximum overshoot and steady state error. Okay, so this is basically one application part. So in the proportional controller part, we have two convenient adjustment has to be made between the maximum overshoot positions and also steady state error and analysis. Okay, next part, this is the derivative control. Derivative control. So derivative control, this is it is basically denoted by the D. D for this is the derivative control actions. So in this derivative control actions, the actuating signals, it consists of proportional error signal added with derivative the error signals also. So I just drawing the pictures, then you have to given the idea. So first input coming, first summing point. This is the first block. This is 1 plus S into TD. This is the another blocks, that is a process or plant to the second order systems also. We know that second order control system in previously we have to discuss the second order system expression, that is omega n square by S into S plus 2 zeta omega n. This is zeta. And then finally we have to calculate it from here output. And here one feedback loops we have to attach, but it is a unity feedback. We know that unity feedback, that means the feedback factor it is also, that is 1. This is summing point, positive. This is the reference input signal. This is the ES. This is the error signal. Okay. And this is the actuating signal. And it is denoted, that is the EA. This is EA of the system. And we know that this is the output. So this is a basically block diagram of the derivative controller part. Derivative or D control. Okay, so in this derivative control part, it is basically we have to design for the second order control system. So this derivative control action, the actuating signals, this is the actuating signals. We know that previously these actuating signals, it is the basically proportional to the error signals. This is the actuating signals. Here we have to denote EA of the systems, and these actuating signals, it is proportional to the error signals also. And error signal, we know that this is the basically difference between the reference input signal to the unity feedback system to this derivative controller part. Okay, so now this actuating signals the actuating signal for the derivative control action, I just express that is a D for derivative. Okay, the derivative control action is given by that is the equation. We know that EA with respect to timing also, that is the ET, error of the system. TD is the constant of the derivative controller part, and we know that derivative controller part, it is being ratio with respect to the timing. So this is the basically derivative controller expressions where TD is constant. Okay, so this is basically expression for the error of the systems of the derivative controller part, that is EAT, this is equals to ET plus TD into DET dt. So this DET dt, that means the changes of the error of the systems, so that's why it is with respect to DET dt. And here TD is the basically constant, that is the derivative time constants also. Okay, up to this part it is okay, all of you?
Yes, sir.
Okay, so we know the Laplace transform. Everyone write your own name and roll number in the chat box also. And Gautam, you present?
Yes, sir.
You take a screenshot, okay? So
Okay, sir.
Laplace transform, we have to apply the previous equations. Of the actuating signal. Incorporating derivative control is, that is the apply to the previous equation in the Laplace inverse transform, that is the EAS, that is equals to also ES plus S into TD, that is the ES, error of the systems. Okay, so this is basically expression of the derivative controller part after you have to apply the Laplace transforms. So that is the EAS, that is equals to error of the system plus S into TD into ES also. Okay, so next class we have to discuss another part also, and we have to also elaborate this derivative controller part in the next classes also. Then we have to discuss the integral controller part and PID controller part, that is a proportional integral derivative controller. Okay, so this is very important. And another announcement for your midterms. So first module and second module, We know that. So first module and second module in your midterm. So in your syllabus, that is module